Hello, this video will cover the software part of my project on creating wireless NeoPixel lighting using the Arduino Nano RP2040 Connect. In this video I'm going to explain about how to use the software on the Arduino to control the lighting through Wi-Fi and a web browser. It will explain about different colour sequences and how you can create your own sequence to match your mood. My previous video explained about the prototyping and how the hardware works. I've also covered some hardware problems that surfaced. I'll be revisiting the hardware in future when I look at creating a PCB, but this video will concentrate on the software side. First, here's a quick recap of the project so far. In my first video, I covered the hardware side of the project. I explained about the Arduino RP2040, which is based around the Raspberry Pi's microcontroller used in the Raspberry Pi Pico, and an ESP32, which is used to provide the wireless functionality. I explained about different designs for the voltage level shift output buffer, and I explained about the one I'd decided, but then disaster struck. In my second video I explained about the design feature, or flaw, depending upon how you look at it. The problem started with a particular LED, but this caused confusion due to the way it behaved and unfortunately resulted in the damage of one of my Arduinos. To avoid this in future, I've decided to use a different voltage level shifter circuit based around a two-stage MOSFET buffer. Please see the link in the description for the project page, which has all the details of the past videos and will be updated with future progress. Please also consider subscribing if you haven't already and click the notification icon to get notified about updates. I've split this video into chapters, allowing you to jump to the relevant part of the video. I've covered the introduction already. Next is the project overview, explaining about the hardware. I then explain why I wasn't able to use the programming language I wanted and the consequences of this, both good and bad consequences. The next chapter gives a quick view into the web interface, although that is covered a few more times in later chapters. I then show the code and how it works. If you're wanting to customize the interface or create your own sequences, then you need to watch that chapter. But if not, then the start of it explains about the configuration files, which is all you really need to get started. Finally, I'll explain about how you can incorporate this into a simple automation, looking at using the Raspberry Pi to turn the lights on and off. As a quick recap, this is a project based around the Arduino Nano RP2040 Connect. This is powered by the RP2040 microcontroller designed by Raspberry Pi, which is used in the Pico. It connects through a hardware level shifter, which then connects to the addressable LEDs, sometimes known as NeoPixels. My initial plan was to write code specifically for the Arduino Nano RP2040 Connect, which is the device shown here. If that had been successful, then it would have been limited to that particular microcontroller. But when I realised it didn't have the support for certain features I was hoping for, my workaround means it's likely to work with lots of different Arduino models. This means the code is not as easy to program as I'd like, but it does have the advantage of making it more accessible to different platforms. It won't work with all Arduino models. As this is a wireless project, then it does need wireless capability. Specifically, it needs to support Wi-Fi NENA library, which should include most of the Arduino IoT models. In addition to the Arduino RP2040, I've tested with the Arduino UNO WiFi revision 2, the Arduino Maker Wi-Fi 1010, and the Arduino Nano 33 IoT. When I come to the PCB, it will be specifically for the Nano format, but you should be able to use the code with the other models. This circuit is still in a breadboard in the prototyping stage. Instead of using the two breadboard LEDs shown here, I've now connected this to a 1 meter long strip using WS2812B RGB pixels. And this allows me to test the proper light sequences. A bit of a word of warning, what follows is going to be quite a technical description. I'm going to try and explain most of the terminology as much as I can, so that someone fairly new to programming should be able to understand the general concept about how it works. But this is written in C++ and it's going to be quite complicated. Feel free to add a comment if there is something that needs further explanation. So my first intention was to write this in MicroPython. I do program in several different programming languages where appropriate, but Python is normally my first choice. There is expected to be a version of MicroPython for the Arduino RP2040 in future, but it was not available when I started the project, and the expected release date keeps slipping by. Whilst you could probably use the version of MicroPython for the Raspberry Pi Pico on the Arduino RP2040, that won't include the network functionality, so it wouldn't be suitable for this project. I therefore decided to program using C++ instead. This is the native language used by most Arduino products. There are some differences in how Arduino uses C++ to how it's used in other compilers, and I'll explain some of these as they are particularly relevant to this project. Specifically, this project is based around the way that C++ is implemented using the Arduino IDE. I'm using version 1.8. It should also work with Arduino version 2. C++ is good and a powerful programming language. If you're just getting started in programming, I'd normally suggest learning Python as a first language rather than C or C++, but most of my early programming was using C. One thing that is difficult to grasp is the concept of pointers, and I have used pointers in the code. But don't worry if they appear alien to you. They can take a while to learn that particular aspect of C programming. This project also needs HTML and CSS to show the web page and JavaScript code used to make this web interface. So you'll need to be familiar with those if you want to make substantial changes to the interface. Before we look at the code, I will say that this is still work in progress at this stage. As a result, I won't be going into too much detail as it's likely to change anyway. In particular, the main loop function is very long. Could really do with refactoring the code to clean it up a little. So that's something I'll be looking at updating in future. One thing I will cover is how the sequence functions are generated. This will allow you to create custom sequences if you'd like to do something that's not included in the default functions. I'll also explain about the URL format, which will be useful if you want to control lighting as part of a home automation project, or turn the lights on and off on a schedule using a Raspberry Pi. If you're unfamiliar with the Arduino, it uses files ending with an extension .ino. These are normally C++ files, but one of the differences in how C++ is normally handled by most compilers is that they're effectively concatenated together at the compiler stage. So this means you can split your program into multiple files, but they're treated as though they're one big file. This is not the way C++ normally works. So individual files are normally compiled separately and then linked at a linker stage. The way that this is implemented on the Arduino can make it simpler when programming, although it does allow for bad habits such as global variables that apply across multiple files. I've avoided that as much as possible, although I have used the define directive, which is used by multiple files, and that's included in the header files. The Arduino uses C-style.h header files, although they are not needed in the same way that they are sometimes needed in other C++ programs. If this all sounds like gobbledygook, don't worry, you don't need to understand all this, but it may be helpful for C programmers that find it odd the way some of the code works. Before I list the files, I'll explain about the feature that I was hoping would be available, but isn't, and how I worked around it. This is in addition to the lack of MicroPython, which, if it was available, may have supported this. The RP2040 has a generous amount of flash memory. This is 16 megabytes on the Arduino, considerably more than the 2 megabytes on the Raspberry Pi Pico. However, using C++, this can only be accessed through your code as though it's raw memory. This is different to MicroPython, which allows you to create a file system and store files in that memory. On the Raspberry Pi forums, there's talk of adding that functionality to the Raspberry Pi Pico, but at the moment you cannot transfer files to the flash memory except through your code. The files I was hoping to serve up include the HTML, JavaScript and CSS files. To work around this limitation, you can include these text files as data in your program and access them directly from the code. This code does not need any image files, but you can even include image files by first converting them to a base64 encoded image and doing the same. Here's a quick look of the web interface that I've created. You will need to know the IP address to connect to, which is something you can configure in the configuration file, which I'll explain later. And this shows a simple interface with various sequences, a speed slider and colour selection. I'll explain this in more details later, but basically you select the appropriate sequence, say the chaser, select the speed with the speed selector, and this is a delay, and choose what colours you want it to display, say red, green, blue, and then click apply. And nothing actually happens until you click the apply button, and then it sets the chaser sequence going. The files used to create the web page are index.html, just a standard HTML file, pixels.js, which holds the JavaScript for the interactivity, and pixels.css, the style sheet for the formatting. As I mentioned previously, these need to be stored as a data string. So they've been put into separate files, each of which has .h appended to the file name. Inside the files, the data needs to be stored as a raw string literal. This just means adding a line at the top of the file, such as the one shown beginning with const char and then the file name effectively as a string variable. Then the closing characters are also required as shown on these. So these are affected with the first or the 3 files required for the web page, and obviously I've missed a section out because they won't fit on the screen. So with that out of the way, we can have a look at what all the different files are. And this may change in future, but it's the structure for now, and I don't plan to change the files for the sequences, which are the ones I'm going to show you how you can customize. From a code perspective, there's these 3 files: Arduino pixels.ino, which is the main executable file, Arduino pixels-web.ino, and the Arduino pixels sequence.ino. Then the HTML files I've already mentioned, index, pixels.js, pixels.css, all appended with a .h. And then a header file called sequences.h, which is used for the sequences, configuration file, config.h, and Arduino secrets.h. This Arduino secrets.h isn't included in the source code. You'll have to create your own, and it just contains your Wi-Fi, SSID and password so that it can log on to the network automatically. If you want to implement this on your own Arduino, then you don't need to understand how the code works. You can just create the Arduino secrets and update the config file, and then you should be good to go. I'll include a link in the description to the website and the files you need to download from GitHub. But if you'd like to understand how it works and how you can create your own sequences, keep watching. If you don't, but would like to understand how you could have the lights come on automatically or integrate this into your home automation system, then you can skip to the chapter on home automation towards the end of this video. Other than the HTML related files, I've mentioned the ones that are needed for sequencers are Arduino Pixels sequencers.ino and sequencers.h. I'll be covering those last in this particular chapter. The main program file is called Arduino Pixels.ino. This imports the Wi-Fi and the NeoPixel libraries. Note, you may need to install these through the Arduino Library Manager. That was covered in the earlier video, and there's a link in the description if you need to go back to that. The code then imports all the other .h files. You need to create your own Arduino secrets.h file, which has the SSID and password for your local Wi-Fi connection. The other configuration file you may need to change is called config.h. This holds a number of pixels on your strip, as well as the LED pin that it's connected to. And then it's got the networking information. Note that the IP address and the related information is separated by commas rather than the period character, which is normally used when you're defining a network. Go back to the main Arduino Pixels.ino file. Much of the loop function is code for receiving the web request and interpreting that. This started out as the example code on the Arduino website used in my previous example, but it's changed significantly since. The most important thing regarding showing the pixels is the last line of the loop, which is highlighted here. This is called every time the loop function runs, and as you can see from the function below, it is used to call the appropriate sequence function. This uses a pointer to the sequence function, which I'll explain later. An important thing is that whenever the sequence changes, then it resets the sequence position, which is this number here. And this is a number which tracks whereabouts in the sequence the program is. This was originally an integer, but I changed that to a long variable, particularly for the older Arduinos, such as the UNO, which removes the upper limit for a 16-bit integer, which would be 32,767. And using a long would just give such a huge number, we don't need to worry about the limit there. This function also handles the timing by reducing how often the respective sequence function is handled. Note that the Arduino does not normally have a real-time clock, so this is based around millis, which is a timer that starts when the Arduino was powered on. It does wrap around after about 50 days, but dropping only one time delay early each 50 days is not going to be an issue for this program. I've moved some of the code out from the main file to Arduino Pixels-web.ino. This is code that relates to the formatting of messages and uses the content of the web.h files I mentioned previously. This was done in order to reduce the size of the main code file, although I may move more into this file when I refactor it in future. So take a look at the web page in a bit more detail. This is important for understanding the way the sequences work. The design and layout may change in future, but this is going to show the main principles of the way the sequences are selected. On the top is the apply button. Note that nothing happens with the LEDs until this is pressed. This means that you can change the sequence and choose your colours without it changing to an intermediate state. You basically get to choose what you want to display and then click apply, and then it starts. Then this section here is the sequences. All you have to do, the very minimum, is to choose a sequence and click the apply button. For instance, if you wanted to turn all the LEDs off, select all off and then click apply, and all the LEDs will go off. And if you want to turn them all on, click apply, and if you didn't have any colour selected, the default is always to have white, so that would turn all the LEDs on white. Next to the apply button is the reverse button. This is a toggle button that typically changes the direction of a particular sequence. For example, if you have a chaser sequence that goes from left to right, this will change so that it goes from right to left instead. The reverse option is incorporated into the sequence, so it's down to how that is implemented in the sequence function, what it does. Then if we look at the part where the sequence are defined, there's 13 shown here, although I have actually implemented more in the code. Some are deliberately hidden. I'll be adding some more in future, as this is the part of the code I've been working on recently. Just to explain a few of these. So all off is obvious, it turns all the LEDs off. All on turns all the LEDs on, which can be just a single colour or it can be a sequence of colours. This is a static option, so the colours will not change unless you request them. Flash is the same as all on, but they all flash on and off together at the same time. And chaser will go from one side of the strip to the other. And this could be multiple colours, which will look like a wave, or you could include black LED, which whenever you include black is effectively the LED is off. That will look like a flash sequence going across the screen. The chaser fill end is where there's a chaser, but then it fills in static LEDs from one end of the strip. And the colour wipe sequences are where the LEDs are normally off and then fill with the colour one LED at a time. Wipe in and out starts from both ends, and wiping starts by lighting the outside LEDs and going inwards. Wipe out goes from the inside to the outside. Note that the reverse on this changes the order of the colours rather than the actual sequence. Finally, for now, the rainbow sequence lights up all the LEDs using the colours of the rainbow and then changes these by moving along one LED at a time. The next part is this speed slider, and this allows you to change the speed of the sequence. The further to the left, the slower the sequence, and moving it to the right will make the sequence run faster. Now, you probably don't want to be using the very rightmost position, as that will be literally running as fast as the Arduino can generate the sequences, and they'll be too fast effectively to see the particular sequence. So the value, which is shown here from the as you change this slider, is actually the delay, and that's what is passed to the code to determine the delay of the code with each iteration. If you move it all the way to the left, that's a delay of 1000 milliseconds or 1 second between each change of the sequence. Effectively, it's the minimum delay, so you will get at least this long between the sequence. If the Arduino takes longer to generate the sequence, then it may be a little bit longer than that. Because of the different Arduinos and their performance, it does not guarantee a particular speed. For some sequences, it makes sense to run them at different speeds. For example, you'd probably want to use the chaser fill end sequence at a faster speed, as it takes a very long time to complete its sequence. The final option is the colours. This is a representation of your LED strip showing only the selected colours. As you can see, it's just showing one at the moment, which is the default of white. But you can click on any of the add colour buttons below and add a new LED in the sequence. So, for instance, click there, I've added red, white and blue. And then this will then be interpreted whenever you press the apply button based on how the sequence works. The other thing you can do is incorporate this black as well. So black effectively means turn the LED off. I'll just remove some of these by just clicking on them. It'll take them off. If I change it to red, black, white, black, and then blue and black, this will mean that only every other LED will be turned on at a time. So again, we can press apply and you can see that happen, and that should give you some understanding of the different things. So we've got the reverse button, the sequence, the speed, and the colours, and that's the information that gets passed onto our sequences. We can now look at the sequence file and see how some of these are coded. First, the easiest of all is all off. This first line of the function defines the function and the arguments that are passed to it, and then there'll be a return value. The arguments are actually ignored for this function, but they still need to be listed for all the functions that are used in the sequence file, whether they're used or not. Returns a long value, which is the sequence position, which is used to keep track of the code's position in the particular sequence. Then basically in the code there's just this one loop which iterates over all the LEDs, turning them off. It uses the set pixel color method and sets them to a color of black, 0 red, 0 green and 0 blue. And after it's finished the loop, it runs strip.show, which actually updates the strip and changes the color. So until that strip.show is called, the LEDs don't actually change color. And then it just returns the same sequence position that it was passed as an argument. In this case, it doesn't update it. The next example is all on. And this is used to turn all the LEDs on based on the colours provided. The function is roughly split into two sections of code depending upon whether the reverse option is set to false or set to true. There are other ways, perhaps more efficient ways of doing this, and I've used those in other sequences, but I used it this way just to keep the code as simple as possible and easy to understand. And if we remove the part where it is reversed, you'll see that we've only got a few lines of code now we need to worry about. So if you just ignore all those that are in dark grey. You'll see it's very similar to the all off function, but instead of setting the colours to black, it uses this array. And this is the array that is passed to the function, and it's a list of all the colours that were selected. And it's also got a value of the number of colours there, so it knows how many colours to display, and then when it reaches the end of those, it resets the colours to 0 and starts again. Again, this particular function doesn't change over time, so it doesn't have the colours changing during the sequence, so it just returns the same sequence position that it was sent at the start. So look at the chaser. First say, I've got a comment that says moves LEDs from left to right, and that may or may not be true. It actually depends what direction your strip is facing, basically. If the first pixel is on the left, then the default is that it moves to the right. But if the first pixel is on the right, then it will move to the left. And if the strip goes in a different direction, say vertically, then it's neither left or right. But that was just to try and explain what happens and how it works. The code is very similar to the all on function that I mentioned previously, except for 3 changes. One is that if there's only one colour specified, then it pretends there's actually two. Colours array is always set to all black initially, and then any colours that are not set in your sequence are set to black. So by doing that, what we're saying is we've got the original colour that was sent, and we'll accept the next one, which is black. And that means if you only send one colour, there'll still be a sequence. The next is that the colour doesn't reverse when the reverse option is selected. Instead, it changes the direction of the movement of the changes. That's handled here. Instead of going up, it goes plus plus down here. If it's reversed, it will go down. So that's set here that if the reverse is not selected, so this is going forward, then we will count down, which will effectively shift to the right for the start position, and otherwise we will count up. And then this function doesn't remember what position we're in the sequence. What it does is it returns that sequence position that's been either incremented or decremented in this one run through this loop, through this function. And then that's the sequence position that gets passed to it. So if this is increased from, say, 0 to 1, then it returns 1, and then next time it will start at 1, increase to 2, return 2, gets passed 2, for instance. And that keeps going on until the number of colours has been reached, in which case it resets back to 0. And that way it's a continuous sequence of lights moving across. This is the basic operation of how these functions work. There are other tricks that can be used. For example, the rainbow sequence actually increases sequence position value much more than one position at a time. And some of the white functions make use of some other functions, so they'll call functions themselves. But I won't go into that much detail of these here. Instead, we move on. As well as adding the program into this Arduino -pixels -sequences.ino, also need to add them to the sequences.h file. In fact, you need to put two entries into here, which I'll show you in a minute. But first, let's just concentrate on these two bits at the start. So you don't need to change these, but these are what defines the requirements later on. So the first entry, which begins with this type def, is a type which is a pointer to a function. Now, pointer to a function is quite advanced C++. As long as you don't want to change the sequence function structure, you can just accept this is needed and moved on. If you do understand pointers, basically this creates as a pointer PFN sequence, which is a pointer to a function, and this shows the arguments that that function expects to receive. And then the next entry is a struct or data structure, which is a way of grouping together different variables that are needed together. You don't really need to understand this in detail, except to follow the sequences when you add the entry to the array of structures, and that'll come clear later. So we will use those to define our new function. And then the next thing is to define all the functions you want to use. This is effectively the same as the first line of the function that was in the INO file, but it's terminated with a semicolon. Instead of having the curly braces and the code in there, it's just a definition. The reason this needs to be here is so that we can include it in the pointer to the structure, in the array of structures, which is what we'll show next. So you just now need to basically copy and paste one of these and make sure you've got the right function name in. And then this is an array of the structure sequence. And each line is one element of the array, which equates to one entry. They all work the same, so I'll just show the one shown earlier so you know how to create these. I'll just take the one all off example. I'll show this. So this is showing the structure that I showed before, which was at the top of that screen, and then this is one of those entries from the bottom. And each of these relates to the corresponding entry in here. So .sequence name is the sequence name we've defined here, and I've put comments here to explain what they are. So we look, the first one is sequence name, and that just needs to be a unique string which should not include any spaces, and this is used to link the HTML entry to this entry. I recommend you use the same as the function name, but all in lowercase, but you could use something different. The title is the text that is used on the button that you click. So this is a short description to the user so they know what the sequence does. The description is used for, say, the tooltips when hovering over a button. So it gives a little bit more detail about what the function does. The group is used to group the sequences together. I've chosen some simple categories. 0 is the basic function, such as all off and all on. 1 is used for the next most common sequences, and it goes up to 4, which are some of the more obscure functions. At the moment, this is just used to exclude any with a value of 4 from appearing on the web page, just to reduce the clutter. But in future, I may look at options to exclude some, or have tabs with different buttons in future. So it really just needs a number between 1 and 4, or 0 and 4, depending upon how popular or how obvious you want this to appear on the screen. And then the final entry is the .seq function, and this is the pointer to the function. And as long as you've created those definitions that came before this, then all you need to do is just set this to the name of the function. Note that this is case sensitive. It needs to be exactly the same as the function name, and unlike the strings, it does not have quotes around it. So you notice all these have been strings except group, which is a number. This one isn't a string, it's the pointer to the function, so it doesn't have quotes around it. So if you've added a sequence to the .no file, you need to add those two entries to the sequence file, sequences.h file, upload it to the Arduino, and then reload the web page. And as long as it has a value of less than 4, which is how it works at the moment, then it will appear as a new sequence option. So those are dynamically created on the web page based on the contents of this .h file. Phew, we got there. I do think the code is much more difficult to describe than if I'd been able to create it in Python, which is one of the reasons I was hoping to do this in MicroPython. But performance-wise, C++ is likely to be significantly faster than trying to use Python anyway, so there are advantages this way. And as I mentioned previously, it also means that it'll work across a range of different Arduino models rather than being tied to the RP2040. So you need a little bit of experience with C++ to follow that code, but you don't necessarily need to understand how all the pointers work, because you can just copy the way the existing entries are made. So if you want to have a go at implementing different sequences, you could just copy one of the existing sequences, have a go at making changes so that it does what you want. As I said, I'll be making some changes to the code in future, but hopefully this should provide an insight into how it works. If you want to understand it better, then follow the link to the source code that I've included in the video description, and try having a go at creating your own sequences. I'm now going to briefly explain how the web interface works and how you can use that for your home automation to bring these lights on automatically. So I've already demonstrated how this web interface works and how you can use that earlier in this video. Essentially, you choose the options and then click the apply button. And this can be used on a computer, with a web browser as I'm using here, or using a mobile phone. But it does need to be on the same network, effectively on the same home wireless LAN. You could make this available through your router to the internet, but note there is no authentication, and what this means is that anyone in the internet could potentially turn your lights on and off. So I'm going to stick with having it only available on the home network. The web interface provides a good way to manually control the lights, but what if you want automatic control? The way the website works is by issuing dynamic HTTP requests. So if we can imitate those in another way, then we can use that to control the LEDs without using the web interface. You can do this by working your way through the code requests and seeing how it's handled. But in this case, I'm going to show you how you can do this using the web interface and then looking at the messages sent to the Arduino. I'm going to do this by looking at the serial console on the Arduino. So with the Arduino connected, you should be able to look at the serial monitor. And if you have this running when you power on the Arduino, you'll see the messages that say it's connected to the network, and it'll also tell you the web page that you need to go to. But if we just do it from here, then we'll just see the new messages that are generated. So the easiest way is to select the light sequence we want through the web page, and then we'll have a look in this console as to what it does. So I'm going to choose a chaser. Already selected. Going to put a selection of colours. Let's reset these. We'll go for the red, white, blue that I used earlier. And then choose whatever speed you want it at, and click the apply button. And you'll see on the console that the query string that is sent to the Arduino is shown here. Always begins with /set, question marks. Seek means this is the sequence chaser, and that is the sequence name that was used in the .h file. The delay used for the speed, whether it's reverse or not, 0 or 1, and then colours is a list of the colours, and in this they're the HTML colours. In this case, FF is red fully on, and then 0 for both the green and blue components. White is all on, and blue is just the blue component. And you could use any HTML colours in there, but it doesn't have the same granular effect. And you can see this by appending this to the normal URL. So if we look, the URL at the moment is 192.168.0.44. That's the one I've chosen for my network. So if I use that and then copy and paste, there's no right click on it, so it's just Control C, and then paste that onto there. Oops. And then if you paste that exactly as it is, then it will just give you the ready status. Just ignore that for now. At the moment that's not used, but by doing this you'll see that I've just recreated that. So now we know that that is the value that we want to use, and if we call that, then we can use that in the automation. The other sequence we'll want is all off, so we'll need to know that one to be able to turn it off. If you just click all off and apply, at at the moment it's still sending these colours because it still sends these colours whether or not they're interpreted by the Arduino or not. So if we just remove those and click apply again, you'll see we've got a slightly shorter sequence. Doesn't matter, but just means that we can reduce the size of the message slightly. And you see that the only colour being shown is the default white, which is FF. So now we can take that and put that into our automation. So now we can look at how we can use that URL from the command line and then in automation. So I'm on a laptop at the moment, but I've got an SSH session here which goes to a Raspberry Pi that I'm using as a home server and some simple home automation. Could be any Linux computer, but for the automation it needs to be switched on permanently, and as the Raspberry Pi is a low power device, it's a good fit here. We use the wget command line tool to demonstrate how you can access the page. wget downloads a web page on the command line basically. Use wget and then put in quotes the URL that we want to retrieve. I'm just going to put redirect the output to a file out.txt so you can just see the result. That's it run. It's run, downloaded it and saved it as out.txt. If we can't get out.txt, you can see it's just got the message ready, which is what it returned. And then you can do the same with the off command as well. And there we go, so that will turn it off as well. And that will allow you to run it on the command line. To do this automatically, I'm going to run update the crontab. There are other alternatives for automation, using systemd for instance, but find crontab is easy to use. So from the command line, just do crontab -e, and this will open up the cron table. Use your default editor, or it will ask you if you want a particular editor. I'm using the Vim editor. You may prefer to use the Nano editor because some find that easy to use. And then on the bottom of this file you'd put when you want it to run. So I'm going to use 020. Just enter this first. So what this says, first one is minutes, so 0 minutes, 20 is hours, 20 is 8 p.m. At 8 p.m, any day of the month, any week, day of the week, so essentially every day, run wget. The output is going to /dev/null, which just means ignore the output, throw it away effectively, and then the page to get. And then to turn it off again, I'm going to turn it off at midnight. And it's the same, but with the off command. And then save and quit. And that's now saved it and loaded it, and it will run that automatically at those times each day. I've already created another video and there's a web page which explains more about creating crontab entries, and there's a link to that in the description. So this video has covered the software side of the Arduino wireless PixelStrip controller, at least the progress I've made so far. It's covered how to use the software, why I wrote the software in C++, and the result of that, particular that it will now work with different models of Arduino, how the software is written and works, how you can add your own custom sequences, and then how you can use the URL in simple automation tasks to turn lights on and off automatically. Next stage, I plan to create a PCB for a more permanent solution, which I'll be doing in KiCad. And I also plan to create an enclosure to mount this as part of my outdoor lighting solution, which I'll be looking to design using the FreeCAD parametric 3D CAD modeler. So if you haven't already subscribed, please do so and click on the notification icon and you'll get notified when I release my next video. Thanks for watching, and then I hope to see you on a future video.